Took a little longer than we wanted. We learned some interesting things, made some very educational mistakes along the way, but now I'm proud to say that we're making some really good progress here on Machine Learning Basics. So the last time we were in the code trying to add features to it, we were going to take our one-dimensional problem and we're going to move it over to 2 dimensions. Now we knew that was going to add a lot of complexity and a lot of challenge. What I wasn't ready for was some of the bugs that we found, some of the issues we had, and the complete insuitability of one of our reward mechanisms. So we've had a bunch of interesting things happen. I'm going to go through, we're going to walk through the code, and we're going to show you the different runs that I've done and some of the results that we got. And so everybody can see what is going on and kind of why. So I'm now calling this my 3 inputs scenario. Originally, I was just going to have 2 inputs, a left rocket and a right rocket, and that you could fire the left rocket pushing your vehicle right and fire the right rocket pushing your vehicle left. It turned out that was too hard to control. So I moved from 2 inputs to 3 inputs. So now there's a main rocket as well as some maneuvering rockets. Now, those maneuvering rockets are rockets, so it's still a challenge to control. However, having that main thruster provide the majority of the thrust centrally along the center axis of the craft has made the whole thing much more stable and actually playable. So if we take a look at our game, we can see that we have our main marker and then we have a left and a right thruster. And so I've put little cubes here to model them. And it looks very much like we had before. We just now have those 2 little cubes, the left thruster and the right thruster. The target is the same, the floor is the same, or very nearly the same. There hasn't been much, if any, changes to that. The biggest change to the floor is that now that this is a 2-dimensional problem, the floor has gotten much, much, much wider because that gives our craft something to crash into. Before it was just a very small platform under the marker, and that wouldn't really work for our little Moonlander game. So, going into the code, we still have the floor script, and all the floor script does is it detects if there's a collision, and if there is a collision, it tells the game that the craft has collided, it has crashed or not crashed, and if it has crashed, it marks the game as over. So, nothing fancy or exciting there. The agent, on the other hand, is significantly different. So we're going to pull that open. Here we go. Come on, Windows. All right. Let me close that and make this bigger. Here we are. All right, so now I have a game object to hold the left thruster and the right thruster, and I hold those so that when I am calculating the physics, I actually add the physics at the location of the left or the right thruster. I have the marker itself, the target that we're aiming for, and the floor that we want to avoid. We have a starting height, min and max, so that is how far above the marker do we want to start our game. The offset, this is actually the side-to-side offset. In this case, we're at -5 to 5. So there's a very large width that we can be spawning in here. That's going to come into play as we get closer to the end of this video. Up force, I defaulted it to 20. I think it's still at 20 in the game. This is the amount of force that that central rocket provides. The maneuver force, that's how much force each of the maneuvering thrusters have. I don't think in the actual game we are using 5. I think that was way too much. Yes, so that was 10 times too much. So right now our maneuver force is 0.5. Our minimum reward distance is 0.1. Our distance scale is 1. This is adjustable, and we're going to get into these a little bit because it's really important for some of the other things that we have learned. How many points if you are really close to the marker? How many points do you lose if there's a collision? And again, I think this is something that we have adjusted to -1 instead of -10. Yes. And then what is the collision velocity threshold? Originally, for the one-dimensional game, I actually had that fairly high. I think I ended up with 3. For this version of the game, because I've added drag to the physics to help the maneuvering work right, it meant that the vehicle was coming in at a much lower velocity. So I've reduced the collision velocity threshold to a much lower number. So it's easier to crash, but you're also not coming in as fast. This is the Boolean that gets marked if there is a collision. This ignore input steps is part of how we got around some of the physics issues, and there is a whole nother video about some of the physics issues that goes more into detail about that. The ignore input count goes along with the ignore input steps. So that's how many do you want to ignore, how many have you ignored. Let's see. And then on reset, this is just an event so that we can call other things if we want to on the reset. When we start up, we just cache the rigid body so that we're not constantly looking it up. These get component calls are a little on the expensive side. They're not too bad generally, but especially when you're trying to speed up your game to 100x because you want to train really, really fast, caching these rigid bodies and things so you're not doing these get components at in your update loops and whatnot is always a good idea. Agent reset, as you know, this is when the game gets initialized. What do we do? How do we set up the vehicle? So again, we try to clear out all of the physics attributes, and then we provide the markers rotation. Again, we mark that as the identity, so we're clearing that out. The target position is anywhere between that left and that right maximum. The markers, that's the target transform position, and then the vehicle position is, again, anywhere between that min and that max, and then also the height is between that starting height min and that starting height max. So the vehicle has, pretty much anywhere, in this size box generally, I think, to spawn. So it's a fairly decent size box that it can get spawned in. And then let's see, and then this ignore input stuff again, that's for the physics bug, and we have a whole nother video about that. So I'll be sure to put that in the show notes so that we know if you're curious about why I'm doing that and what the physics bug is. It had something to do with the input and the physics system bleeding over, and so I had to do some research as to how to solve that. Collect observations. So now we're moving in 2 dimensions. So in this case, instead of just one distance to the target, we have 2 distances to the target, right? The x and y distance to the target. The current x velocity as well as our current y velocity, that makes a lot of sense. The distance to the floor is still just the difference in the y, so that's the raw distance to the floor at this time. In a future version, we're going to be doing some active sensing of the floor using raycasts, so that's going to look a little bit different. And then this is the z rotation of the vehicle. So because we're moving on the xy plane, the z rotation is the left-right rotation of the marker as it tries to get to the target. The agent action. This is, again, part of that ignoring input for the physics, just burning one frame so that we ignore the input so that the game initializes right. And then we're just making sure that it's continuous state space, so that's pretty much the same as before. Okay, so now instead of one action, we have 3 actions. The left thruster, the right thruster, and the up thruster. Now, these all look pretty much the same, right? The input from the brain can be anywhere from -1 to 1, and that's actually important because that means that each one of those rockets isn't just a downward-facing rocket, it's also an upward-facing rocket. So it's kind of a rocket-retro-rocket pair. And what that means is you can do things like pull off a SpaceX landing when you land on your head instead of your behind. And so that is really interesting because we actually see that show up. I'm super thrilled to show you guys some of this because it's really neat because I didn't expect it at all. So left thruster, right thruster, center thruster, each of those can thrust up or down from -1 to 1. And now again, the maneuvering thrusters, the left and right thruster, that is modified by the maneuver force, which is 0.5, and then the main thruster, I believe, is at 20. So that is the main up thrust. And yes, so the up force is still 20. And so again, the machine can say either go full up or full down, that it has control, and so it uses this up force. The fact that I have -1 to 1 as the range was actually a mistake. I meant to change that to 0 to 1, but when I started watching what it was doing when it was training, I totally left it in because I think it's even more cool than if it was just 0 to 1. All right. If there is a rigid body, which there should be at all times, but I always do my null checks just to be safe. This is where we start adding forces to the vehicle, right? So this is the main up. And so what we're doing is we're getting the transform and the markers in the up direction for that marker, and we're multiplying that by the amount of thrust. So that's up force by the amount that the computer requested that we add. And then we add it to the, again, the center marker transform position. So again, what we're doing here is with this marker, we want to be in line with this center of mass because this is our main thruster. So it'll go directly up. And so it's applying the force in this box's relative up position along that center of mass, from the center of this cube. Similar thing for the left thruster and the right thruster. So with the left thruster over here, it's applying the force at this location, which is going to create a right turn effect. And then the right thruster, if it thrusts up, again, it's going to push in the left direction. So I can show you what this looks like by switching over to the player, and I'll just play a game real quick. So here's an up thrust, and unlike before, I get a consistent up motion, and if the game resets while I'm pressing the up key, it will properly go up. So that physics bug is resolved. And now you can see that I can go left or right and doom my craft to a early demise almost invariably. Well, except for every now and then I land it beautifully like that. So that's all there is to it. For the player controls, I only have a binary thrust at full or not. But the computer, instead of having binary keys, it is given the range, right? So it basically has 3 floats that it can go from -1 to 1, kind of like 3 joysticks, if you happen to have 3 thumbs, 1 for each of those thrusters. All right. If there's a collision, then we set the collision to on collision points. And again, we ignore the input for a little while. We say we're done. And then if we didn't collide, then we calculate the reward and we set the reward. And we had some issues with that. So now our visualization code is a lot better because it provides a lot more information, because I was having issues trying to figure out why the heck my thing wasn't training. And really the main answer was my positive reward area was too small and I wasn't finding it right for a lot of cases. So again, my calculate reward, I have this logically removed from a lot of the other code, right? So that I can pass in parameters. This is what I use for visualization as well. So this code is both used internally for the evaluation, but because I've encapsulated it a little bit, I can also reuse the exact same code for the visualization, which is really helpful. And then this collision happened. Again, this is set to true if the floor detects a collision. That's all there is to this. And it's a silly amount of code, fairly small compared to the amount of effort that went into it, because we did a lot of refining. And then some of it was also adjusting our parameters. And our reward function, by the way, does look a bit different because they had a problem. So in this case, our reward function, I figure out the distance between the marker and the target. Now, this is in 3 dimensions. We're only using 2 of them. They're always in the same z depth, so that kind of goes away. But what's nice is that we could reuse this in 3 dimensions with no modification. We multiply that by a distance scale, which I think in this case is 0.1. And then we also do a max of the distance and the minimum reward distance. Again, this is so that we can't get infinitely close to the reward and cause the math to kind of break. And then what we do is we take a value of 1, we square the distance, and then we multiply that by our on marker points. So basically, the further away you are from the marker, the lower your value is going to be. And in fact, you can get negative here. And so we put in this max of 0 to value to prevent that from going negative, because that's how we accidentally made the self-destruction machine, which is another separate video that I go into much more detail about what the self-destruction machine was and how I accidentally created it and how it's a problem and how you fix it. So there it is in a nutshell. So I'm going to go through the basic brain, and I'm going to move this over to our internal brain. And I have a bunch of different bytes values. These are all of the outputs from the project as I tried various training scenarios and configurations. And so I want to go through each of these a little bit. So the first one here, this is the buggy pass 1. So this is back when I still actually had the physics bug. And this was just the first training run that I did. I wanted to see how it did. I could see that it was trying to do something. You know, it was getting closer generally. It just needed more training. So, I mean, that was nice, but not good enough. So then I have this buggy pass 2, and I let it run for a lot longer. Again, this system still had the physics issue in it. However, what was interesting is it was able to overcome that physics issue to a certain degree. So you'll see as it starts off here, it's spinning. And in a lot of cases, what it's trying to do is counteract the physics bug that started off in the application. But you'll also notice it lands, and it lands a lot. It's gotten very reliable, and sometimes like there, oh, it got closer and now it's marching away. Look at that. You'll get these strange little behaviors. Again, some of that was due to the physics bug. So I went through and I had that issue with the physics bug. One of the things that was happening is it would spin to the left and spin to the right. And the downside was that, you know, it would crash and you get these strange behaviors. The upside was it actually forced the ships to the markers to explore the space more because it didn't have a choice. And so it was able to stumble upon the reward functions. This is the first training that I did when I eliminated that initialization bug. And what we find is this system has learned very clearly how to not crash, right? And all it does is it takes off and it goes up, and it has learned how not to crash. And it, you know, the episode length went right up, and that was better than anything else that it could figure out to do, because, you know, early on it learned not to crash, but then it got too far away from the marker. Part of the problem here was that the reward area for that marker was too small. So I'm going to turn on, we have a new visualization code. And so this visualization code, I'm going to just go ahead and turn that puppy on. And I believe my distance scale was originally a 1. And I'm going to hit play on this. And so you'll see these dark cubes are a reward of 0 or near 0. And then the lighter and lighter you go, the more points that you get. And you can see that the reward area for this was very, very small. And so it wasn't finding it at all. If it did find it, you know, it just wasn't a statistically significant number of times. So that's why in the distance scale, we now have this 0.4, and you'll see that there's a much larger area. And that helps the marker find a positive reward target. And so that helped a lot. Of course, in the very early version of this, I also still kept the negative value where that you could actually earn a negative reward if it got too far away. Well, let's see here. And so that was version 2. And so what version 2 learned, I'll turn the visualization off again. Version 2, this was the one that was the self-destruct machine. This was the one that realized that the negative reward out in the you're too far away to earn any points zone was far worse than the negative reward for crashing. So it would rather crash than earn a negative score by being too far away from the marker. And again, there's a whole separate video on that if you want to learn more about that, because I do go into a bit more depth. And then let's see here. Ooh, adding that to there won't help me. There we go. So now, version 3 is where we have the new reward function with the larger area. All right, so this visualization is appropriate for the reward function for this brain. So we can see all of a sudden this is a whole lot more encouraging, right? It's flying over, and sometimes it has some control issues and sometimes it crashes. This is, I believe, after 500,000 rounds of training, and look at that. That was beautiful. So let me turn the visualization off. And I'm also going to zoom in the camera a little bit. Because this is fascinating. I love this result. And the reason I love this result is because for some reason, it has learned to land upside down. I have no idea why. Right? And this is the kind of thing, when I first heard that SpaceX was landing rockets on their head instead of their tail, I was stymied as to why they did that until I saw some diagrams of the ballistic trajectories involved, in which case it made a lot more sense. In this case, I think it's a very similar thing, right? It's actually hard to get that bottom of the craft facing down again after you've been maneuvering. So it's actually a little easier to get the head over. But what's interesting about this is it also flips almost always counterclockwise or anti-clockwise, depending on where you're from. And I'm not sure why, because even when it's not in its best interest, it'll sometimes, flip counterclockwise like that. When a clockwise flip would have been more energy efficient. And then again, that could be because it just had 500,000 training runs in it. So then I went ahead and ran it for a lot longer. Now, what was interesting about this is even though I ran it a lot longer, it didn't get that much better. It got a little better, but it didn't get way better. But you'll see it make some crazy long shots like that. Sometimes it still crashes, sometimes it doesn't, sometimes it runs out of time, right? But that was a beautiful landing, very close to the mark, so it's doing very well. The other thing that you'll see every now and then, and I don't know why this is, and I'm not seeing it in this session, but I've certainly seen it before, where it will find a point and then just kind of hover there. And I have no idea why it would hover, right? Look at this giant long shot, and then it tried to reel it back in. Now, one of the things that's going on is this is trying to get the best score it can with the time it has. And we provided these machine learning algorithms with only 250 steps. When we are in a one-dimensional problem, it was a very short problem, and so 250 steps was plenty of time. Now with some of these larger scenes, because there's a lot of distance on the X and the Y to traverse, I think it's having some issues just because we haven't given the system enough time to actually complete the task. I think the task is longer than a 250 step. So I'm actually going to crank it up to 500 steps. I haven't done this before, so I'm going to see, maybe we're going to need additional training, and I think we will, because again, it's trying to solve as much as it can in those 250 steps. There we go. There's that hover behavior. I don't know why it does that. I think it's very fascinating. So I'm probably going to do one more just quick little update of doing this training with 500 steps instead of 250. But I'm very pleased to see this interesting emergent behavior come out of the system. I think this is loads of fun. So where are we going to go from here? I want to retrain with 500 steps instead of 250 because I think we will actually see some different behaviors as it's able to have enough time to really complete the task and optimize its solution a little more. I think from there, the videos, this I think is an excellent opportunity to get into imitation learning. And I know that's something that people want to see. And then there's also the sensing piece of it, where instead of us just telling the vehicle how far away it is from the ground, if we are able to put a raycast on it, and then it's sensing where the ground is so that we can move into having uneven terrain, so that it's actually trying to actively avoid the terrain instead of right now where it just has to stay above a certain altitude and land at a certain velocity. So there we are. As always, if you have any questions, thoughts, comments, please feel free to put them down in the comment section. I also now have a Patreon page to help support this project. So if you're interested in supporting this video series, please consider joining the Patreon. Otherwise, like, share, all of those are super awesome and helpful, and even just you watching has been a great joy to me. When I started this project, my personal rule for when I thought it was going to be a success was when there were more people spending time watching it than it took me to make it, right? So that if my total view time was longer than the total time it took me to create it, I would be thrilled. And we've far exceeded that. So I'm absolutely tickled of all the support and engagement that people have shown and how positive this little community has been. So thank you very much. And I'm looking forward to keep creating great things together. So have fun out there and happy learning.